Welcome back. In this video, we will learn the metrics that are used to characterize the performance of networks. There are limits to the data rate that can be sent over a link. We will learn about these limits. By the end of this video, you will know what metrics are used to analyze network performance, how to calculate latency on a link, and what is the maximum achievable data rate on a link. A number of very different link technologies exist for connecting nodes. Some of these we have discussed before. However, since we are ultimately interested in exchanging data over the network, we should be able to only care about transmitting data without knowing the details of various link technologies. Link abstraction refers to ignoring the implementation details and instead characterize a link by performance metrics such as latency, data rate, and error rate. The performance of a network is important because it strongly affects the performance of networked applications. Bandwidth is one of the fundamental performance metrics. It is also called data rate. Bandwidth of a link is the number of bits per second that can be transmitted over the link. Advertised bandwidth usually corresponds to the maximum value. Therefore, the measured data rate is usually lower than the specified bandwidth. The measured data rate is called throughput. As a caution, note that bandwidth also refers to the width of frequency band. As we will see towards the end of this video, these two definitions are related, but they are not the same. In any case, the unit of bandwidth when referring to data rate is bits per second, and the unit when referring to the width of a frequency band is hertz. Before continuing our discussion of performance in computer networks, let us briefly get familiarized with the convention of units that is used in computer networks. First off, we are going to use capital B to indicate byte and a small b to indicate bit. By convention, we use powers of 10 for data rate. 1 kbps would mean 10 to the power 3 bits per second. That is 1000 bits per second. 1 mbps would mean 10 to the power 6 bytes per second, which is 8 million bits per second. However, we use powers of 2 for data size. Therefore, 1 kilobyte is 2 to the power 10 bytes, right, and not 10 to the power 3 bytes. Similarly, 1 megabyte is 2 to the power 20 bytes. This can get confusing when both of these conventions are used simultaneously, which is not infrequent. We will actually get in this situation when we will calculate delay in the next few slides. So one may see, for example, instances where one is referring to transferring 1 megabyte file over a 1 mbps link. And this statement is referring to transferring 2 to the power 20 bytes of data over a link of bandwidth 10 to the power 6 bits per second. Bit width is another way to represent bandwidth. A 1 Mbps link would transmit 10 to the power 6 or a million bits in a second, and therefore it takes 10 to the power minus 6 seconds or 1 microsecond to transmit each bit. On a 1 second interval, this bit takes 1 microsecond space, and this is called bit width. As bandwidth increases, the link fits more and more bits in 1 second interval, which causes the bit width to shrink. Thus, bit width on a 2 Mbps link is half microsecond, and that on a 4 Mbps link is a quarter microsecond, and so on. Latency is the second fundamental performance metric. Latency is also referred to as delay. Latency means the time it takes a packet to travel from the sender to the receiver. The latency on a single link has two components: propagation delay and transmit time or transmission time. Propagation delay is the time that signal takes to travel from the source to the destination. From the laws of physics, nothing can travel faster than light, and in most cases we are talking about electromagnetic wave being the signal, and therefore propagation delay is given by the link length divided by the speed of light in that link, which is approximately 2/3 of the speed of light in free space in copper and fiber links. The speed of light in free space is 3 times 10 to the power 8 meters per second. The second component of latency is transmission time. Transmission time is function of data rate or bandwidth, and it is defined as data size divided by data rate. Often we are interested in round trip time. Round trip time is defined as the time it takes for a message to go from sender to receiver and then receive the response back from the receiver back to the sender. Note that one-way delays can be asymmetric, hence using this relation that round trip time is twice one-way delay is only an approximation. Ping command tells us the round trip time. When A pings B, then this ping message from A goes to B, and B sends an echo of that message back to A. Let us try to ping IETF and see what happens. And as the replies come, it's showing the round trip time. So the first message took 92.1 milliseconds, second 95.8 milliseconds, third 89.7 milliseconds. As you can see, we will also talk about jitter in today's lecture, and you see these numbers vary from message to message. At the end, it outputs ping statistics. All in all, 9 packets sent, 9 received, and this is the minimum, average, maximum, and standard deviation statistics for our round trip time. And those numbers for this run of ping was 84.2 milliseconds, average was 90.2 milliseconds, maximum was 96.5 milliseconds, and the standard deviation was 3.8 milliseconds. Now let us calculate latency for these two examples. In the first example, we have a data of 1 byte. It's being sent over a 230 meter long, 80 kilobits per second copper link. For this example, the propagation delay is the length of this link, which is 230 meters, divided by the speed of light in copper, that is 2.3 times 10 to the power 8 meters per second. This gives us 10 to the power minus 6 second, or 1 microsecond. The transmission time would be the size of data, which is just 1 byte, that is 8 bits, divided by the bandwidth, which is 80 kilobits per second, that is 80 times 10 to the power 3 bits per second, and this gives us 100 microseconds. And so the latency is 1 microsecond propagation delay plus 100 microsecond transmission time, and that is 101 microsecond. In the second example, we want to calculate the latency when 1 kilobyte data is sent over a 200 kilometer long link that is running at 100 megabits per second, and that's a fiber optic link. On this link, the propagation delay would be the length of the link, which is 200 times 10 to the power 3 meters, divided by a speed of light in fiber, which is 2 times 10 to the power 8 meters per second, and this gives us 1 millisecond. The transmission time would be the size of data, that's 1 kilobyte, that would be 2 to the power 10 bytes times 8 bits, divided by the bandwidth, that's 100 Mbps, and this gives us 8192 times 10 to the power minus 8 second, or 0.082 millisecond. So the latency in this case is 1 plus 0.082 millisecond, which is 1.082 millisecond. On LANs, the propagation delay is usually much smaller than transmission time, and on highest speed long links, it's the transmission time that is much smaller than propagation delay. When a packet goes from source to destination through one or more intermediate nodes, there is a third component of latency, which we will call queuing delay. Although strictly speaking, queuing delay is the time that a packet spends in buffers waiting for getting forwarded. Here we are lumping all the delays at switches and routers as queuing delay. For the two metrics, bandwidth and delay, their relative importance depends on application. For the applications that send small messages, latency becomes important. A low latency, low bandwidth link for these applications is preferable to some high latency but large bandwidth links. However, applications that transfer large amount of data, bandwidth becomes important. In these applications, large bandwidth has a great impact on reducing the transmission time, which in turn keeps the latency small. I leave it as an exercise for you to work out the latency when 1 gigabyte file is transmitted over these two links. You can assume that these two numbers, 1 millisecond and 100 millisecond, are propagation delay. Delay bandwidth product is useful when designing networks. We can think of the channel between a pair of processes as a hollow pipe, where the delay is the length of this pipe and bandwidth is the diameter of this pipe. Then the product of delay and bandwidth gives the maximum number of bits that we can put in this pipe, and that is the number of bits that can be in flight at any given time. Consider example of a long distance link where delay is 50 milliseconds and bandwidth is 100 megabits per second. On this link, the delay bandwidth product is going to be 50 milliseconds, that is 50 times 10 to the power minus 3, and 100 megabits per second, that's 100 times 10 to the power 6 bits per second. And this product is 5 times 10 to the power 6 bits, or 625 kilobytes. That's quite a bit of data. Why care about delay bandwidth product? Delay bandwidth product gives the amount of data that the sender must transmit before the first bit arrives at the receiver, if the sender wants to keep the pipe full. In some cases, the sender waits for signal from the receiver that the receiver is receiving the data. In this case, it takes another one-way latency to receive a response from the receiver. In other words, the delay is now equal to 1 round-trip time. And therefore, in this case, the sender needs to send one whole round-trip time times bandwidth worth of data before it stops to wait for a signal, if the sender wants to fully utilize the network. Network bandwidth has been increasing. This increase reduces transmission time, because transmission time is function of bandwidth. However, propagation delay is altogether a different story. Propagation delay would remain affected because, as I said earlier, propagation delay is governed by the speed of light, which remains fixed. To consider or to understand the effect of latency better, let's consider transmitting 1 megabyte file on these two links. One is 1 megabit per second link and the other one is 1 gigabit per second link. Both of them have same length. The round trip time on both of them is 100 milliseconds. On this lowest speed link, the file will take 80 round trip times to transmit. However, on this highest speed link, it cannot even fill the pipe. It looks just like a packet. Therefore, 1 RTT is just about 1% of the total transfer time on this lowest speed link. But on this highest speed link, RTT is 100% of the transfer time, and therefore latency dominates on highest speed networks. To appreciate the effect of round-trip time on highest speed networks, let us consider an example of file transfer request. We know that throughput is equal to transfer size divided by transfer time. Now suppose one round-trip time is spent on requesting the file and setting up the file transfer, and therefore transfer time is equal to round-trip time plus transfer size divided by bandwidth. Now we are going to put this back in throughput equation, and that gives us effective throughput, and that is equal to transfer size divided by round-trip time plus transfer size divided by bandwidth. And now, just to make this concrete, let us suppose that the transfer size is 1 megabyte and bandwidth is 1 gigabit per second and round-trip time is 100 millisecond. So putting these numbers here, this is equal to 8 times 10 to the power 6. Round-trip time is 0.1 second plus again 8 times 10 to the power 6 divided by 10 to the power 9. This is bits per second, and this thing gives us 74.1 megabit per second. So the impact of round-trip time is to decrease the throughput from 1 gigabit per second to an effective throughput of only 74.1 megabit per second. The effective throughput tends to bandwidth in large data size limit. And to see that, let us look at this equation again. In large data size limit, the second term, which is the transmission time, is going to dominate the first term, that is propagation delay. And so as this goes up, we can approximate effective throughput by transfer size divided by transfer size divided by bandwidth, and that is bandwidth. Jitter is a performance metric that is important for time-sensitive applications such as audio video streaming, conference calls, sensor actuator loops, and real-time applications in general. Jitter refers to variations in latency. Although the sending process may generate packets at regular intervals, the operating system and queuing delay variations cause these packets to arrive at the receiving process at irregular intervals. Jitter can have mild consequences for audio-video conferencing and streaming kind of applications, where one can use buffering to smooth out the effect of jitter. However, jitter can have serious consequences in time-critical applications like cyber-physical systems. It turns out that we can't send data at arbitrarily high rate on links. Nyquist limit specifies the maximum data rate through perfect noiseless channel. Channel is a more general term than link. For example, storing data on a DVD and retrieving it later on is a channel. These results are not limited to only links, and therefore we are going to use this term channel. This limit is due to Harry Nyquist, who was an engineer at Bell Labs in the US. In 1928, Nyquist established this fundamental theorem that says that a signal with bandwidth B Hertz can be completely reconstructed by sampling at 2B Hertz. A consequence of this theorem is that if a signal is passed through a channel of bandwidth B, the frequency components higher than 2B get filtered out. This means that a binary signal cannot be sent through the channel at more than 2B bits per second. In general, for M-level signals, the maximum data rate is given by 2B log base 2 of M bits per second. As I said, where M is the discrete levels of the signal. Using a different method based on physical considerations, another engineer also at Bell Labs, Hartley, established that the maximum data that can be sent on a link in time t is proportional to 2b times t times log m base 2 bits. Nyquist made many big contributions. His work led to the foundation of information theory by Claude Shannon 20 years later. This is a good place to revisit NRZ. Recall NRZ encoding that we learned in a previous video. Suppose we want to encode 010010. In the NRZ encoding that we saw earlier, we had two signal levels, low and high, and we encoded 0 with low and 1 with high. So this NRZ encoding of 010010 is going to look like low followed by high followed by low followed by another low followed by high and followed by low. So this is 0 1 0 0 1 0. The Nyquist limit for NRZ with two levels will be 2b times log base 2. We have two signal levels, so log base 2 that is 1, so this is 2b bits per second, right? So this is the maximum rate. In the case of NRZ with 4 levels, we can encode 2 bits using 1 level. Suppose we use this convention of these 4 levels, 6 volts, another level, 4 volts, 2 volts and 0 volt, and we encode 1 1 using 6 volts, 1 0 as 4 volts, 0 1 as 2 volts and 0 0 as 0 volt. Then our NRZ encoding of this bit sequence is going to look like, so first we will encode 0 1 and that is 2 volts, so the first 2 bits are encoded like this. Then the next pair of bits is 0 0, right? So next is the lowest level, and then the third pair is 1 0 and that would go to 4 volts. So this would be NRZ encoding with 4 levels, and in this case the Nyquist limit gives the maximum rate as 2b times log base 2. Now we have 4 levels, and that gives us 4b bits per second. Nyquist's limit was for noiseless channels. In reality, all channels have noise. In a groundbreaking paper titled A Mathematical Theory of Communication, Claude Shannon laid the foundation of information theory in 1948. He is called the father of information theory. Like Nyquist and Hartley, he was also working at Bell Labs when he published this work. Later on, he joined MIT, where he remained till retirement. Shannon built many machines. This is one of his many machines. He created an electromechanical mouse that could solve this maze. This maze could be rearranged and the mouse could be placed anywhere in this maze, and the mouse would reach the destination, which is somewhere here. Shannon showed that reliable communication is possible in a noisy channel. The maximum achievable data rate through a channel, which he called capacity, is given by this expression, which is the bandwidth times log base 2 of 1 plus S over N, where S is the signal power and N is the noise power. This ratio of signal to noise is very common, and it's usually given in decibels. So this S over N has another symbol, SNR. So SNR in decibel is 10 times log base 10 of this ratio of signal to noise power. And by the way, this decibel, this unit, is in honor of Alexander Bell, who invented the telephone. Here is an example to illustrate Shannon limit. Suppose we want to know the capacity of a 10 kilohertz link where the signal to noise ratio is 30 decibels. So rewriting 30 decibels as 10 log base 10 signal to noise ratio, we get signal to noise ratio as 10 to the power 30 divided by 10 is 3, and therefore the capacity is bandwidth times log base 2 1 plus signal to noise ratio, and that is 10 kilohertz. So this is 10 to the power 4 times log base 2. This is 1000. 1000 plus 1 is 1001, and that is approximately 100 kilobits per second. If you could change signal and noise levels on this link, how would you improve its capacity to, let's say, 1 Mbps? I leave it as an exercise for you to think about it. Here's a summary of this video. We learned 3 metrics: bandwidth, delay, and jitter. Bandwidth is synonymous with data rate on a link. Often this bandwidth is that is advertised is not what is achievable, and therefore we also have this measured data rate that we call throughput. The second metric we learned is delay or latency, and this is sum of three components: propagation delay, that is determined by speed of light and the length of link; the transmission time, that is determined by data size and bandwidth; and queuing delay, that is the delay that a packet incurs at intermediate nodes. We also saw a concept of delay bandwidth product, and delay bandwidth product gives the maximum number of bits in flight that can be in a link. We also saw that the maximum data rate that can be sent over a link where the link is perfect, it has no noise, is given by this Nyquist limit, which is twice times the bandwidth times log base 2 of m bits, where m is the number of signal levels. And lastly, we saw the Shannon limit of the capacity of a channel in presence of noise, and the capacity is given by the bandwidth times log base 2 of 1 plus the signal to noise ratio. For further reading, I highly recommend reading biographies of Nyquist, Hartley, and Shannon on Wikipedia. The material we covered in this video is discussed in Peterson and Devi in Chapter 1, Section 5, and in Tenenbaum and Weatherall's book, Chapter 2, Section 1. Here is a short quiz for you. You might want to pause this video. The correct options are A, B, and D. A, that is propagation delay on a given link, is fixed. That's correct. Second, jitter is caused by varying queuing delays at routers, and that is correct. That is the source of jitter, at least one source of jitter. On highest speed links, the transmission delay is the dominant component. That is not true. Actually, this is the propagation delay. So that D is also correct. We can see that by applying Nyquist formula. So Nyquist formula says that the maximum rate is given by 2 times bandwidth, which is 3 times 10 to the power 3 Hertz, log base 2 of 8, that is 3. So that is 2 times 3 times 3 times 10 to the power 3 bits per second, and that is 18 kilobits per second. That's all in this video. See you next time.